Great. Thanks everyone for joining us on this talk as part of the Tech Talk series. And today we're going to be looking at smart, effective and efficient offshore wind design. It's a quick summary of what we'll cover today. I'll give a bit of a background of where we're at in the offshore wind industry, some of the challenges facing the industry, then look quickly at Kent's experience in offshore wind design so far, and then the bulk of the session will focus on some of the tools we've been developing and are now successfully deploying on projects to address some of these challenges. Starting then with the offshore wind industry at the moment, a series of graphs here, and I don't want to focus on the detail, but looking at the trends. Here we see top left the installed capacity of offshore wind farms, historic trend and future predictions. In the middle, looking at water depths for sites being developed for offshore wind farms. And on the right-hand side, looking at the turbine size for these wind farm developments. Again, not focusing too much on detail, but what you can clearly see here is the trend for massive growth in these areas. And conversely, if we look at the cost side of the industry, bottom left, levelized cost of energy for developed and planned wind farms, and then in the middle bottom, strike price recently agreed in auctions worldwide, and we can see the cost base has to continue to decrease to remain competitive. So overall, we've got the twin pressures of growing complexity and scale and challenge in the designs, and needing to achieve this all whilst continuing to drive down costs. I don't think Lewis Carroll quite had offshore wind in mind when writing Through the Looking Glass, but a quote here that I think sums up the challenge nicely. It takes all the running you can do to keep in the same place. If you want to get somewhere else, you must run at least twice as fast as that. And that, I think, sums up where we're at in the industry and looking at design of offshore wind farms now. We need to switch from running harder to running smarter. So looking a bit at some of Kent's designs and how we've seen that play out so far in the industry. If we look back to some of our pioneer projects, the likes of Dudgeon with the largest monopiles at the time, Beatrice, the deepest jacket, Triton Knoll, the first wind farm with the Pisa foundation rules and the largest turbine at the time. We saw great designs, great projects, breaking new ground in terms of what's possible, bringing a lot of the oil and gas offshore structures design experience into offshore wind, and pushing forward what we can do. Then if we move into more current projects, the likes of some Brio Oriel and some XL monopile development work, we've seen a step change in what's possible through software solutions, the use of cloud computing, being able to now run integrated load analysis in-house as a designer, having templates and processes set up, being able to do bespoke designs for each position in a wind farm. There's been a step change in capability. And looking forward, as I've touched on the last slide, to continue this pace of growth, we will need to continue to accelerate what we're doing. So to sum it up, I think we've moved from a time of having smart people doing designs through moving smart processes, and now we're in an era of smart tools. So what do I mean when I'm talking about smart tools? Well, if we look at just a typical generic offshore wind development timeline here, I think we're probably all familiar with a change curve like these I've superimposed here. So the ability to influence a project obviously highest at the start, and the cost of making any change the lowest, and these flip over, so the inverse is true later in life during installation and operation. So really we focused on the front end of the of the process here, and today we're just going to touch on 3 of the tools Kent have been developing to give a snapshot of what's going on. So first, looking at the very front end, field optimization with the virtual wind farm tool. Then MODOT, our design optimization tool, into concept and start detailed design, and then in a bit more detail through detailed design, some of the toolkits developed. So as I say, starting at the front end, field optimization with a virtual wind farm tool. So the challenge when you've got a site to develop, got the boundary, know what it needs to be, how do you plan out a wind farm there? Some images here on the left of what this might look like if you focus on a single discipline or single attribute to develop the farm. So for instance, top left, if you looked purely at energy yield, then having turbines well spread out across the whole site gives you the best results. But conversely, say in the bottom right there, if you focus purely on a transmission objective, then having a tightly packed array, well aligned, close to shore, gives you the best results. Now, either one of these would be possible, but neither really offers the best overall position. So the challenge is finding that balanced view that meets or balances effectively all the criteria and might result in something like the image on the right here. So how does the virtual wind farm tool do this? Well, it's software here bringing together full range of inputs, parameters, factors that influence the design, and then pulling all this together to look at that balanced solution. So here, able to look in real time at making changes, seeing sensitivity studies, seeing the impact of those changes on the CapEx and OpEx and overall levelized cost of energy of a wind farm. An example then of where this has been used in recent US seabed lease auctions. So we were able to support a client with providing comparisons across sites, looking at optimal design configurations very early in the process, and supporting some sensitivity studies looking at changes in various inputs and the impact that would have on the levelized cost of energy. So a huge benefit being able to have this information upfront and particularly able to see very quickly the impact of changes. Moving on to our multi-objective design optimization tool, MODOT. Now, our next session on the Tech Talks will touch on this a bit more detail, looking at its application to some floating offshore substation work. But as a brief summary here, this is all about an automated workflow, being able to chain together a range of our analyses and then interfacing that with artificial intelligence and advanced optimization algorithms. So we're now able to run through thousands of load cases, design configurations, much faster than we ever could manually. And using these optimization algorithms, able to get to a much more efficient structure, a much more highly tuned structure than we could do previously. So some examples of what that might look like. Up in the top, an example looking at plotting 2 objectives against each other and seeing the relationship between the two, and this so-called Pareto front that shows the actual limit of that optimization that's possible. Another example in the middle here of mapping a design space, looking for a monopile here at how the can diameter and embedment depth affects the natural frequency. So being able to very quickly plot out across the whole design space of interest what the kind of sensitivities are and what areas are useful to focus in more Or an example in the bottom right, looking at natural frequency for a monopile with diameter and mass. So being able to hone in on what is possible and what the best solution is. So an example of this being used on a recent project is for the external work platform design around a monopile. So here we were able to take a concept already developed and run it through our MODOT tool and achieve a 45% reduction in steel weight there through optimization of the beam layout and also section sizes in the platform. So here being able to run that optimization while keeping the constraints and a sense check around fabrication ability. So not having totally bespoke section sizes for every member, but having the right balance there. And then if I move on and hand over to my colleague Dave, we'll talk a bit more about the jacket toolkit.
Briefly talk about our jacket toolkit. Our jacket toolkit is a collection of in-house and third-party software that we've developed with the aim of streamlining the design process for WTG jacket foundations. The toolkit covers all stages of the jacket design, so both uncoupled analysis, which is typically done more at the start of concept or feed designs, and also to support the detailed design. But then as well, the more intensive and detailed coupled analysis process that is performed at later stages of the design. The toolkit is, as I say, built around third-party software. This is mainly DNV's CSAM software, which is specialist offshore structures, finite element, and associated packages. We've also recently started performing in-house integrated loads analysis in support of or in lieu of WTG suppliers being able to provide external load iterations. So yeah, the toolkit is under continuous development. And one aspect of that that's ongoing at the minute is incorporating and streamlining the in-house ILA process. The benefits of the toolkit is to reduce manual activities and the time waiting on analysis. It gives improved quality control through reduced manual tasks. There's less chance for human error. And yeah, the main benefit is that there's going to be more time for doing the engineering. And this figure on the right here just shows some of the aspects of it at a high level. As I say, the core computation is done with third-party software, CSAM or bladed, but what we've developed are in-house tools for streamlining the pre-processing, post-processing, model building, visualization aspects of the process. Next slide, please, David. So I'm just going to talk a bit about three case studies, three projects that we've worked on. Starting with Beatrice, which we designed, what was it now, five or 6 years ago, and is now operating. It's been operating for a few years. So back in the day when the Beatrice design started, we were manually building the models and running the models using ASAS at the time. So this is before we moved to using DNV CSAM software. And we were using localized computing resources. So that is effectively just people's desktops sat under desks or chaining together whatever we could. And the results of these kind of manual processes and limited computing power was that we had to take a bookending approach to the design. So that was looking at the softest or stiffest locations only in a cluster. And for the coupled analysis, we had to perform a process of reducing the number of simulations to a set of representative simulations, so that the amount of computation was manageable, because the time history analysis that is required for the coupled analysis is very computationally intensive. Then we move into Sombria, where it was a few years later, and that's recently been completed, but still some outstanding detailed design activities ongoing as the jackets are fabricated and installed. But the improvements we made as we were kind of working on this project and in parallel to was we've started using a tool called Jacket Builder, which I'll talk a bit more about in subsequent slides. But this is effectively a parametric scripting tool, which is we have developed to bolt onto CSAM software package. This is also where the Jacket Toolkit started to become apparent as its own kind of named entity. And it was also where we started using cloud computing rather than just using localized computing resources. The outcome of this is that we were able to do uncoupled analysis on all 62 of the jackets, which has been great for doing sensitivity studies and optimization of particular aspects, especially the foundations where there's a lot of variability between the different sites. It also meant that with the cloud computing especially, we could do coupled analysis for a full DLC table, so hundreds or thousands of simulations from multiple models, and complete that towards the end of the project when we were fully up and running with this. Complete those in hours or days rather than the weeks that it was initially taking. Another tool that I'll talk about on a subsequent slide briefly is LINDAM, which uses influence matrix assessments instead of the standard parametric FMU equations, which were developed for oil and gas structures. And the outcome of that is optimized weld improvement, reduced or completely removed in certain locations. And then finally, briefly moving on to the Oriel project, which we've just recently completed the feed design for. This is the kind of first feed design project for jackets where we've used our in-house integrated loads capabilities. So there was no external load iteration loop with the WTG supplier. We just had initial loads at interface to verify our own loading against. And we have a few models internally that we use, concept models, which are representative of commercially available turbines. The one we used here was a 16 megawatt, 240 meter direct drive turbine, and that was analyzed in bladed. And yeah, we've been developing our processes throughout the project, and as of now, we were able to turn around the ILA in a single day, which is significant improvement on even what we've managed to do on some rear. The main saving there is that there's a reasonably significant amount of turnaround time for the external iteration process with the WTG supplier. And then just in summary at the bottom here, we've got just kind of the key outcomes of the development as time has gone on, and we've been able to leverage improved computing power. So we've got reduced conservatism, high confidence, reduced timescales, and again, more ability for doing the engineering. Next slide, please, David. So very briefly, just a bit more information on the Jacket Builder tool, which is kind of one of the key things which allows us to do a lot of the improvements we've seen on through Sombria and onto Oriel. But it's again using CSAM Genie software and the associated packages for structural analysis and hydrodynamic analysis and post-processing. But we have got a comprehensive set of parameterized inputs, which is able to generate the 62 different foundation models with the varying stick up, different soil conditions and soil springs, and rapidly create a model with very limited manual input time. And then it automatically creates things you need for post-processing or the input files for the coupled analysis. And this has been a real game changer in terms of how much time it takes to assess models, and it has been what's been able to enable us to assess every single jacket in a wind farm. And then if you move on to the next slide, please, David. I'll just talk briefly about LINDAM, which stands for linear damage. And this is another one of our tools in our toolkit. And this is a tool for performing joint fatigue assessments, which would otherwise be typically performed or historically has been performed using parametric equations, which have been empirically derived from testing and finite element analysis, but mainly or only on oil and gas structures. And there's a few kind of subtle differences with offshore wind foundations, which means that these aren't completely appropriate, and there's some workarounds for that. But LINDAM allows for more representative substantiation through detailed local modeling, so either in shells or solid elements. Is the screenshot on the right here, where you analyze the stress concentration factors directly. And it follows the DNV codified approach, which has been implemented in Python for efficient processing. And we've got a bit of a workflow at the bottom here, which shows how it takes the hundreds or thousands of time history analysis input files. It takes the local Abacus model, which unit load cases are applied to, and then our tool combines the two in order to calculate the total combined damage at hotspots all around the joints. And this visualization on the right here is actually a damage contours around the circumference of the joint, which allows for very refined weld improvement if that is required, such as toe grinding, etc. Or in some cases, depending on the improvements you see compared to the parametric formulations from FMU, you may actually be able to remove weld improvements altogether. And yeah, that's it from me. Thanks, David.
Thanks, Dave. So just to wrap up in summary then, as we look at offshore wind design now and look into the future, we've seen a rapidly developing industry that needs rapidly developing capability to keep up with the ambitions. We've touched on some of the tools taking advantage of these new improvements in software developments, artificial intelligence, and optimization. So the virtual wind farm tool, setting a project off on the right foot, and then MODOT and the jacket toolkit, able to make significant savings in time and steel weight through a design process. And really, it's this use of smart tools that's essential to being able to meet the growing demands of the industry. And a final quote to wrap up from Steve Jobs, that this innovation is really the ability to see change as an opportunity, not a threat. And it is this rate of progress that makes it such an exciting industry to be part of at the moment. So thank you very much for listening to our presentation. And if there are any questions, please do reach out with the contact details on the screen there. Thanks, everyone.